I have my system given here. There's some important givens and equations we're going to need for this. So we know the length in the wires here, AE and CF, is going to be 1/16 of an inch. The modulus of elasticity for both wires is going to be 29 times 10 to the 6 psi, as well as the force P here is going to be 120 pounds downward. For this problem, we're going to need our delta equation, as well as our three equations of equilibrium. To start, we can identify that this is a pin-pin connection, meaning we're going to have two reactions, one in the y and one in the x, as well as these two pins here, we can identify as two force members. So drawing the free body diagram for that, we're given this. Starting with the first equation of equilibrium, we're going to have f of x is 0, and our only x in this situation is going to be ax, so we know ax equals 0. F of y equals 0. We know that FAE plus FFC plus AY, doesn't matter which direction you draw AY, is going to equal 120 pounds. Can't draw now. Pounds. These two equations can be important if you're asked to find the reactions. However, in this problem, we are asked to find the tension in cables EA as well as FC, and the deformation at point B. So we aren't going to need it in the end, but it's still good to write out. So I lied, that's point D. So finding the moment about point D, we know that's going to be equal to 0. And we are going to be going in the counterclockwise direction. So our force Fc is going to be 8 inches away, meaning our equation is going to look something like force of Fc times 8, go off the free body diagram, plus our 120 pound load. Sorry, let's rewrite that. It's going to be plus the force of member AE, which is going to be times 24, is going to equal our 120 pound load times 16 inches. And we can see here that this is actually a 3-to-1 ratio. So here's our 1, here's our 3, and here's our 2, meaning our moment about the D, point D, is FFC plus 3 FAE equals 240 pounds. So this is going to be our equation 1, and we are going to need to remember that. And now we are going to use our delta equation. Delta equals the force times the length over the modulus of elasticity times the area. So knowing these, we are actually going to have to use a little bit of trigonometry here. So thinking about this logically, we know that there's a force here pushing down on the entire system. So it's pretty safe to assume, don't know what just happened, pretty safe to assume our deformation is going to look somewhat like this. So here's our original member, and in some form or way, because of that force here at P, this is what our new system is going to look like. So finishing out the triangle. So we're just going to call this here point A. So we have our A and our A prime. And our A prime is going to equal our delta A. So now we're going to also have our P. So it's going to be B as well as B prime. And our point C, which is going to be C prime. Putting units, we know that this is 8 inches, this is 8 inches, and this is 8 inches. Meaning we can use similar triangles to determine a ratio between them. And using our original moment equation, we can combine the two to find our indeterminate solutions. Because this is a 3-to-1 ratio with our given distances. It won't always be this simple, but you can still use the same concept. So we know that point A is going to be 3 times the distance of point C, which is our 2 cables. So we know that the force, sorry, the delta of member A, I believe it was AF, is going to be 3 times the distance of delta, there's EF, or AE and FC. AE and FC. So writing out our delta equations, we have delta of AE is going to equal the force, which is FAE, because we do not know that yet, and that is what we're going to be solving for. Times the length of member AE, which is 15 inches, times our modulus of elasticity, which is 29 times 10 to the 6th, 6, times our area, which we actually haven't calculated yet. Would be good to calculate. Our area of the wire is going to equal pi over 4 times 1/16 squared. So I'm going to find the area and be right back. Okay, so here we have found our area for the wires, so I've plugged it into the equation already. And we know that delta AE is going to equal 3 times delta FC, which is going to be FC times, I believe it was 8 inches in length. So when you're taking your deltas for these, you have to use the length. So EA was 15 inches and FC is 8 inches. So times 8 divided by 29 times 10 to the 6th times 0.00307 inches. And we can see here that we can actually cancel out our modulus of elasticity as well as the area. So we didn't truly need to find the area, but it is good to know just in case. So these cancel out completely. So our new equation is going to be 15 FAE is equal to 24 FFC. So that's going to be our equation 2. And going here, we're going to copy this equation really quick, move it down so it's a little easier to look at. So these here are 2 equations. So this is equation 1, this is equation 2. Doesn't matter how you want to solve this. I'll probably go and solve for FAE because I can just plug it in. So FAE going to equal 24 over 15 FFC. So now we know a relationship between FAE and FFC, and all we have here is FFC and FAE. 2 unknowns, 2 equations, meaning we can solve now. So FAE, so our new equation is going to be FFC plus 3 times 24 over 15 FFC equals 240 pounds. So I'm gonna find our two unknowns and we'll be right back. So I found our two forces, and this is actually the answer to part A, finding the two tensions in the cables. So we know that FFC is pushing in this direction, as well as FAE is pushing in that direction. FFC with a force of 41.38 pounds, and FAE with a force of 66.208. So the last part of this problem was asking for the deformation at point B. So we can go back to our original equation, uh, sorry, our similar triangles, and we know that uh, delta B here is going to be twice the distance of delta C. So delta C, we know, is going to be, delta C is delta FC. So it's going to be FC, which we found, times the length, which is 8, divided by the modulus of elasticity, times the area. This is why the area was important. We didn't need it in the original equation, but in order to solve part B of the problem, we did. So we know that is equal to 2 2 delta C. So dividing by 2, I apologize, I did this backwards. C. So delta B is going to be 2 delta C. So we have, I'm just going to distribute this 2 into the 8 here. So we have 16. FFC is 41.38 pounds, dividing by the modulus of elasticity times the area of the wire is going to equal our delta B, and finding this will give us our solution, so I'm going to, okay, so working that out, we now know that delta B, or the deformation at point B, is going to be 7.437 times 10 to the negative third, or 0.0074 inches. And that's going to give us the solution to this problem. The two things we were looking for were the tensions, which we have found here, as well as the deformation at point B. Some important things to know and to remember is to, first of all, find your two equations. Your moment, that should be given, statics, and your similar triangles here. Like I said, you don't need the dimensions to be 8. You could find the ratio between all of the dimensions and all of the points. But just identifying this relationship right here was the most important thing. Relating these two to each other and getting our final equation, which gave us the possibility to solve, gave us our tensions, and then calculating the deformation at B was pretty easy with just plugging in numbers into our delta B.